You know, it's funny. I use a calculator all the time, but I've never really stopped to think about what's actually going on in there. Like, how does it know what to do with all those numbers and symbols we just throw at it?
It's a bit of a magic trick we take for granted, isn't it? But behind that magic is this fascinating world of expression evaluation.
Expression evaluation.
Yeah, the rules and processes that computers use to solve, well, mathematical expressions.
Can this expression evaluation, it's not just about calculators, right? It's a kind of fundamental to how computers think more generally.
Absolutely. At their core, computers are really just very fast calculators. They're manipulating information according to a set of instructions. And understanding how they do this, even with something as simple as a math problem, can unlock some really surprising insights.
Okay, now you've got my attention. Where do we even begin with unpacking all of this?
Well, let's start with that calculator example. Imagine you're solving a simple expression like this. Open parentheses, 1 plus open parentheses, 2 plus 2, close parentheses, close parentheses, plus open parentheses, 3 plus 4, close parentheses.
Okay, so, yeah.
Seems pretty straightforward, right?
Yeah, basic arithmetic. The answer is 12 if my mental math is still working.
Exactly. But even in this simple example, right, there are choices to be made about the order in which those calculations are performed.
I guess so, yeah. You'd probably solve what's in the parentheses first, right?
You probably would, based on what we learn in school about order of operations. But a computer has to have those rules explicitly programmed into it. And interestingly, those different possible orders of calculation aren't just about getting the right answer. They're also a way of visualizing something quite profound, causal relationships.
Hold on, causal relationships, like cause and effect. Are we suddenly talking philosophy here?
Not exactly philosophy, but a concept that bridges both computer science and physics. Think of it this way. Each step in solving that equation, each little calculation, is like an event. And just like events in time, some events must happen before others. You can't add 2 plus 2 until you know what 2 plus 2 equals, right?
Okay, that makes sense. But I'm still not quite wrapping my head around how this relates to computers.
Well, we can visualize these dependencies, these causal relationships, using something called a causal graph. Imagine each little calculation in our expression as a box, right? We can draw arrows between those boxes to show which calculations depend on the results of others. So in our example, the box representing 2 plus 2 would have an arrow pointing to the box representing 1 plus 4, since you need the result of the first calculation to do the second.
So it's kind of like a flowchart for math, showing the necessary steps and their order.
Exactly. And what's fascinating is that these causal graphs, they don't just apply to simple arithmetic. They can map out the flow of information in all sorts of complex computations.
Okay, I'm starting to see how this goes beyond just calculators, but things get a bit more interesting when we bring in more complex calculations, right? Like,
Precisely. Take, for instance, the concept of recursion. This is where things start to get really mind-bending.
recursion. That rings a bell. It's those functions that kind of like call themselves, right? Like the Fibonacci sequence.
Yes, the Fibonacci sequence is a perfect example. It starts with 0 and 1, and each subsequent number is the sum of the two preceding ones. 0, 1, 1, 2, 3, 5, 8, and so on. To calculate, say, the 8th Fibonacci number, a computer uses that recursive definition, creating this complex web of calculations.
I vaguely remember this from math class. It always seemed kind of magical, the way the sequence just like appears.
And that magic is beautifully illustrated by the causal graph for a recursive calculation. If you were to look at the causal graph for calculating the 8th Fibonacci number, you'd see a much more intricate network of relationships, with calculations branching out and converging in a very specific way.
So are you saying that the way a computer calculates something like the Fibonacci sequence actually has a visual representation?
Yes. And within that visual representation, something fascinating emerges. We start to see dot space.
Wait, hold on. Space, like physical space. As in, my calculator contains a tiny interdimensional portal.
Not physical space, no, but a kind of abstract computational space. You see, to calculate something like the 8th Fibonacci number, the computer doesn't have to compute every single number in the sequence, like in order.
What do you mean?
Well, let's say we break down the calculation. To get the 8th number, we need the 7th and the 6th. But to get the 7th, we need the 6th and the 5th. Notice how the 6th Fibonacci number appears in both of those calculations.
Okay, I see. We need the 6th number for both the 7th and 8th.
Exactly. But we don't need to calculate the 6th number twice. We can think of it as existing independently, calculated once, and accessible for both the 7th and 8th number computations. It's as if these calculations are happening at different points in a kind of computational space, just like events can happen simultaneously at different points in our physical universe.
Wow. That's kind of mind-blowing. So you're saying the way a computer figures out a math problem might actually have parallels to how our universe unfolds in space and time?
Precisely. And it gets even more interesting when we start exploring different ways to slice up those calculations, much like physicists talk about different reference frames in the universe. But I think that's a good place to pause for now. We can delve into those mind-bending connections in the next part of our deep dive.
Okay, so last time we were venturing into the realm of computational space and how it relates to, well, actual space.
Yeah.
I have to admit, my curiosity is thoroughly piqued.
It's all about perspective, isn't it? Just like in physics, where different observers might perceive the order of events differently depending on their relative motion. That's Einstein's theory of relativity.
Right.
There are different valid ways to kind of experience a computation.
All right, you're going to have to break this down for me.
Sure.
How does Einstein figure into how a computer crunches numbers?
Remember the causal graphs we talked about? Those diagrams that map out the dependencies in a calculation? Imagine drawing lines through that graph, kind of like slicing a cake, right?
Okay.
Each slice represents a set of calculations that could happen, simultaneously.
Okay.
A snapshot of the computation at a particular moment.
Okay.
These slices are called foliations of the graph.
Okay, I vaguely remember those different timelines we saw earlier where some calculations happened at the same time and others were in a different order.
Right.
Is that what you mean?
Precisely. Each foliation represents a valid way to experience the calculation. Just like different reference frames in physics represent valid ways to experience the universe.
Okay.
What one observer sees as simultaneous might appear sequential to another.
Right.
And both viewpoints can be correct within their own frame of reference.
So a computer working through a problem is like its own little universe, and we're the ones choosing how to observe it.
Yeah.
That's a pretty wild thought.
It is, isn't it? But there's a key difference.
Okay.
In our universe, the laws of physics are, as far as we know, constant, right? With computers, we can tweak the rules, create entirely new systems of logic, and explore how those changes affect the computational universe we're observing.
So it's like we're not just observing this computational universe, we're also the architects of it.
Exactly. And that brings us to another fascinating aspect of computation. What happens when there isn't just one path to a solution? There are multiple possibilities.
Okay.
This is where we enter the territory of what's called multiway evaluation.
Anti-way evaluation, multiple paths to a solution.
This sounds intriguing, but I'm having a hard time picturing it.
Sure.
Can you give me a concrete example? Absolutely.
Yeah.
Let's say we have a simple rule that any number can also be replaced by twice its value.
Okay.
So a 1 could become a 2, a 2 could become a 4, and so on, right?
Okay.
Now let's evaluate the expression. Open parentheses, 1 plus 1, close parentheses.
Okay, that's easy enough.
Yeah, it's 2. True, in the traditional sense.
Yeah.
But with our new rule, things get a bit more interesting.
Okay.
We now have choices to make.
Okay.
We could apply the doubling rule to the first one, giving us open parentheses 2 plus 1, close parentheses, which results in 3.
Right, I see that. Or we could double the second one,
Right.
making it open parentheses 1 plus 2, close parentheses, which also equals 3.
Precisely.
Yeah.
And we could even double both ones, giving us open parentheses 2 plus 2, close parentheses, which equals 4.
Right.
So we now have 3 different paths we could take, all stemming from the same initial expression.
Wow, so even a simple calculation can branch out into multiple possibilities.
Exactly.
It's like that Robert Frost poem, The Road Not Taken, but for math.
Yes, exactly.
Is there a way to visualize this, to see all these different paths?
There is, and it's called a multiway graph,
Okay.
just like our causal graphs. But now instead of a single line, we have branches representing each possible decision point,
Okay.
each alternate path the calculation could take.
Sure.
In our open parentheses 1 plus 1 close parentheses example, our multiway graph would start with that expression and then branch out to show all 3 possibilities. Open parentheses 2 plus 1, close parentheses, open parentheses 1 plus 2, close parentheses, and open parentheses 2 plus 2, close parentheses.
So it's like each path on this graph is a different possible history of the calculation, a different way the math could have unfolded.
Precisely. And what's even more interesting is that some of these paths might lead to the same result.
Right.
In our example, both open parentheses 2 plus 1, close parentheses and open parentheses 1 plus 2, close parentheses lead to 3,
Right.
while others lead to different outcomes.
This is really making me rethink how I see even the simplest equations. So we've gone from calculators to spacetime to this idea of a multiverse of math with all these different possible paths.
Yeah.
My brain is starting to hurt a little, but in a good way. What does this all mean? Why does it matter that there are multiple ways a computation can unfold?
That's the million-dollar question, isn't it? And the answer might just change how we think about everything from the design of artificial intelligence to the fundamental limits of knowledge itself.
So last time we ended on a real cliffhanger.
Uh-huh.
We were talking about multi-way evaluation, this idea that even a simple calculation can have multiple paths, multiple possible histories.
Right.
It's fascinating, but I'm still trying to wrap my head around why it matters.
It's like anything else, really.
Okay.
Once you realize there's more than one way to look at something, it changes your whole perspective.
Okay.
In this case, thinking about computation in terms of multiple paths has some, profound implications.
Like what? Give me an example.
Well, imagine you're trying to design a better artificial intelligence.
Okay.
Instead of creating an AI that can only follow one line of reasoning,
Right.
what if you could create one that explores multiple possibilities simultaneously?
So instead of our AI being limited to a single path, it could consider all the different branches on that multi-way graph, all the what-ifs.
Exactly. That's
Yeah.
the potential of multiway computation.
Okay.
It allows us to move beyond linear thinking and explore a whole range of possibilities that were previously hidden.
Okay.
It's like going from a single train track to a vast network of railways, opening up this whole new world of potential destinations.
That makes sense.
Yeah.
But are there any practical applications of this idea? Or is it mostly theoretical at this point?
It's becoming increasingly practical, actually.
Oh, that's
We
good.
see it in fields like drug discovery,
Okay.
where researchers are using multi-way algorithms to simulate how different molecules might interact,
Oh.
exploring a vast number of possibilities to identify, promising drug candidates.
So instead of testing each molecule one by one, they can use these algorithms to explore multiple avenues simultaneously.
That's amazing.
It is.
Yeah.
And it's not just about speed. Multi-way computation allows us to tackle problems that were previously considered unsolvable
Right.
because of their complexity.
Right.
Imagine trying to map out all the possible moves in a game of chess.
That would be impossible, right? The number of combinations is astronomical.
Precisely. But with multi-way computation, we can start to explore those vast spaces of possibilities,
Okay.
identifying promising paths and discarding dead ends much more efficiently.
Wow, so this isn't just about math or calculators anymore.
Right.
We're talking about, a whole new way of thinking about problems, about
Yeah.
computation itself.
Exactly.
Yeah.
It's about embracing the inherent ambiguity and complexity of the world
Right.
and realizing that there might not always be a single right answer,
Right.
but rather a spectrum of possibilities to explore. It's kind of humbling, isn't it? We started with this simple act of typing an equation into a calculator, and we've ended up contemplating the very nature of computation and its connections to the universe itself.
And that's the beauty of a deep dive like this, right?
Yeah.
It reminds us that even the most mundane aspects of our lives are connected to, profound ideas.
Yeah.
And that the quest for knowledge is an ongoing journey full of unexpected twists and turns.
I have to say, this has been an incredible journey. I'll never look at my calculator the same way again.
And that's really the best outcome, isn't it? To leave this conversation with a sense of wonder and a thirst for further exploration.
Absolutely. Well, on that note, we'll leave you with this final thought to ponder. If even the simplest equation can have infinite possibilities, what does that mean for the limits of computation and the limits of what we can understand about our universe?